We've seen that an integral calculates a pretty important quantity, a signed area between the graph of a function and the x-axis. And so it would be really nice to have some shortcuts for calculating integrals, or some tricks just to give us some flexibility in how we calculate integrals. Right? It's a bit tedious to always have to use the limit of a Riemann sum definition because that gets messy fast. Fortunately, there are many shortcuts for calculating the values of various integrals, and we'll look at just a few here. I'm not going to prove these in terms of the limit definition of the definite integral, but you can prove these all in terms of the limit definition. It's not that hard, except for the last one, actually. But I will give you sort of good geometric ideas for why these facts are all true. So for the first one, the integral from a to a of f of x dx is 0. If you think about the graph of a function, right, what this integral is calculating is the area above the single x value a. So this is the area of just this single line segment. But a single line segment doesn't have any area, and so this area ought to be 0. All right, for number 2 here, the integral from b to a of f of x dx is the negative of the integral from a to b. Now this seems a bit strange at first because, after all, shouldn't both of these just be the area between these two x values? Shouldn't those be the same? Well, the difference between these two integrals is what you get when you write down delta x for these two integrals. For the integral on the left, remember delta x is always the top bound minus the bottom bound over n. So for the integral on the left, that's a minus b over n. And for the integral on the right, delta x is b minus a over n. And you can see that because these differences in the numerators, because these differences in the numerators are the negatives of each other, these integrals will also be the negatives of each other. So this one is the negative of that one. So the upshot of this is you can actually reverse the order of the bounds of integration if you want to, as long as you remember to throw on an extra minus sign. All right, number 3 here, the integral of a sum is the sum of the integrals of the original two functions. This should be plausible because, after all, an integral is built out of a limit of a sum. But sigmas distribute over sums, and limits also distribute over sums. That's the sum rule for limits. But an integral is just a limit of a sigma. So both of these distribute over sums, and so an integral should also distribute over a sum. Exactly the same goes for differences. A sigma and a limit both distribute over differences, and so an integral should also distribute over a difference. Number 5 here, same idea. If you have a constant multiple inside of a sum or a limit, you can move that constant multiple outside. But an integral is built out of a sum and a limit, or a limit and a sum, and so you can move constant multiples outside of an integral. Notice that it is important that this multiple be a constant. If this were another function of x, this would not be true at all. But if you have a constant multiple inside an integral, you can just move it outside. All right, the last item in this list isn't totally obvious, so it's a pretty confusing formula. The integral from a to b of f of x dx is equal to the integral from a to c plus the integral from c to b for any choice of c here. This is true as long as your function has integrals, as long as all of these integrals actually exist. But if you actually draw a picture of what's going on here, it looks a lot less mysterious. So let's draw a picture of this integral on the right. On the left. So here's our function. It's an integral from a to b. And so the integral on the left from a to b is the area of this entire region. Everything below the graph, above the x-axis, to the right of a, to the left of b. What about the integrals on the right-hand side? Well, for this first one, that's the integral from a to c, and c is somewhere in the middle here. Actually, it doesn't need to be in the middle. It could be over here, and this is still true, but it's easier to see if you put it in the middle. So the integral from a to c is the area of this blue region. The integral from c to b, well, that's the area of this red region on the right. And if you add together the blue and the red region, you get the whole region. So this complicated looking formula or fact or property of integrals really is just saying that if you have two separate areas that don't overlap, when you put them together, the total area is just the sum of the two, which is pretty obvious when you say it that way. But with the integral notation, that obvious fact looks like this formula. To see how these properties of integrals can be handy for calculating integrals, let's look at an example. So let's calculate the integral from 3 to 7 of x squared minus 3x plus 2 dx. In addition to the properties of integrals from the last slide, we'll also use these two integrals. So both of these you can work out using the limit definition of the integral. Just use the limit of a Riemann sum and grind through all the terrible algebra, but I've done that ahead of time, and this, in fact, is what you get. So let's go ahead and calculate this integral. Now this integral, the integrand is made up of a sum of terms, and so we can distribute the integral across all of the sums. So we get the integral from 3 to 7 of x squared minus the integral from 3 to 7 of 3x plus the integral from 3 to 7 of 2. And I've forgotten some dx's. Don't forget your dx's. Okay. Now in the middle integral, we have a constant multiple here, this 3, so we can move that outside the integral like that. That's going to make things a little bit easier. Now, if you look at these first two integrals, that's exactly what these integral formulas tell us what we get, so we can use the integral formulas. For this first integral, that's the second integral formula. So it says that the integral of x squared is 1/3 times your top bound, 7 cubed, minus your bottom bound, which is 3 cubed. Minus 3 times, and now we can use this first integral formula. We get 1/2 times your top bound, which is 7 squared, minus the bottom bound, which is 3 squared, plus, for this last integral, I don't have an integral formula written down for it, but if we interpret this as an area, this is from 3 to 7, and it's the constant function 2. So this is a rectangle that's 2 high and 4 wide, and so that area is going to be 8, 2 times 4. All right, and now we can just work out all of this arithmetic. You see, we've sort of done the calculus part. We've actually finished computing the integrals. It's just a matter of working out all of this arithmetic. So 7 cubed, I don't have that one memorized. So 343 minus 3 cubed is 27, minus, let's see, 3 halves times 7 squared is 49, minus 9, plus 8. And then we can punch this all into a calculator or do the fraction arithmetic ourselves or however you like. So this is 316 minus 3 halves times 49 minus 9 is going to be 40 plus 8. So 316, is that divisible by 3? No, of course not. So 316 over 3 minus, here we can simplify, 3 times 20 is 60 plus 8. So negative 60 plus 8 is going to be negative 52. So 316 over 3 minus 52 gives us 160 over 3. All right. So this integral, if we had tried to use the limit definition of the integral, the limit of a Riemann sum, this would have taken all day. But using the properties of integrals and a couple known integrals, it actually wasn't that bad. And we get a result without too much work. There are a few other properties of integrals that are worth looking at. In particular, it's nice to have some way of having a rough idea of what an integral is, even if you can't calculate the integral. What we'll see is there are lots of integrals that are just too difficult to calculate, and it's nice to have some idea of what the integral is without knowing exactly what it is. So what we're going to do is figure out a way to come up with an upper limit and a lower limit for the possible values of the integral, for some unknown integral. And what we're going to do is approximate the area that we get from this integral using just a single rectangle. So to get this started, let's draw what a function might look like, so something like this. And let's have some x values, so say we're going from a to b, like this. And if we use a single rectangle to approximate this area from A to B, there's really no question about how wide the rectangle should be. The rectangle should go from A over to B. And so the width of the rectangle is going to be B minus A. All we need to do is choose a sensible height for the rectangle. So there are many heights you might choose, but if we want to come up with a lower bound for this integral, if we want to come up with a lower limit that this integral definitely is not smaller than, the sensible thing to choose for the height of our rectangle is the smallest height. If we want to know how small the integral might be, we should choose the smallest height on the graph. And that's right here. Just to give this value, this height, a name, let's call that little m. So little m is the minimum value of f of x on the interval from a to b. And if f of x is a continuous function, then the extreme value theorem guarantees that there is a minimum value. So if we choose this for the height of our rectangle, then our rectangle looks like this. And we can write down the area of this rectangle. The height of it is m, and the width of it is b minus a. And so the area is m times b minus a. But look, the area that we were approximating, the area under the graph, the red rectangle fits inside of the region that we started with. So that means that the red rectangle, its area is definitely smaller than the integral. So m times b minus a is less than or equal to the actual area, which is the integral from a to b of f of x dx. And this is what I mean by a lower bound. We've found a value that you don't need to know the full function f of x to compute this value, but it's some lower limit on what the integral is. The integral has to be bigger than this. It can't be smaller than this. So this is a lower bound. Well, to get an upper bound, you can bet that, well, if we chose the smallest height before, we should choose the largest height to get an upper bound. So let's look at the maximum value of the function. So that would be here. Let's call that capital M. So capital M is the maximum value of f of x on the interval from a to b. And if we use this maximum value for the height of our rectangle, that gives us this blue rectangle. And the area of this blue rectangle is the height, which is capital M, times the width, which is b minus a. And if you look at the region that we started with, the black region down here, it fits completely within this blue rectangle. But that means that the area of the black region has to be smaller than or equal to the area of the blue rectangle. So that means we can put a less than or equal to in here. And that makes capital M times b minus a an upper bound. The actual value of the integral has to be smaller than capital M times b minus a. So now we have an upper and lower bound for the value of this integral. And the nice thing about having this sort of upper and lower bound is these things on the end, right, the actual value of the integral is trapped in between them, but they're easier to calculate. And sometimes that's good enough. So let's look at an example of using this upper and lower bound idea. Let's find an upper bound for the value of this integral, the integral from 0 to pi of sine of x dx. Now, this integral is something that we definitely do not have the tools to calculate exactly, at least not yet. If you graph sine of x, of course, from 0 to pi, it looks like this. And if you wanted to use the limit of a Riemann sum definition to find this area down here, you'd end up with some weird stuff inside of sine, right? You'd have sine of a plus I times delta x. Now a is just 0, but I times delta x is going to be I times pi over n. And then how do you find a big sum of that kind of thing? I mean, who even knows? That sounds pretty bad. So that seems pretty hopeless. But we can find an upper bound because, remember, to find an upper bound for the integral from 0 to pi of sine of x dx, our upper bound says that this integral, whatever it actually is exactly, it has to be less than or equal to the maximum value of this function, but that's 1 because we're talking about sine here. So the maximum value is 1, times the width of this interval, which is pi minus 0, because it's pi on the right and 0 on the left. So that's pi. So this integral, we don't know its exact value, but it definitely is no bigger than pi. Also, it's no less than 0, because the minimum value of the sine function on this interval is 0. So we don't know exactly what this integral is, but it's definitely between 0 and pi. And we were able to figure that out without actually having to calculate any integrals, which is a pretty neat trick.